So in previous class, uh, I, I said that about Faraday's second law. Faraday's second law, where I say that Zn M copper mass of copper divided by mass of Zn equal to equivalence of mass of Zn and equivalent mass of copper. Where I draw the pictures like this, and let's say the electrolytes is here, and I simply connect like this. Okay, and but since that it is wrong, because since we are taking two different types of electrolytes, so this graphs will be not like graph will be like this. Sorry. Actually picture will look like this. So let's say this is CuSO4 and this is ZnSO4, and this rod is copper rod, this is Zn rod. So also same Zn. This is anode. So we will connect like this: positive charge, negative. So this is positive charge, sorry, anode. No, this is positive, this second positive, this second negative. So this will we connect here negatives, and this we connect any resistance. Okay, so picture will look like this, and where mass of Zn equal to mass of Zn upon mass of copper equal to look at equivalent mass of zinc upon equivalent mass of copper. Okay, this is the corrections. Like this diagram is not wrong, this is correct picture. So next we will study the terms of electrolytic cells. Electrolytic cell. This is first term is resistance. So we are very familiar with the term resistance. Resistance means which oppose the flow of electrons. So before that, let me clear one thing. Suppose two electrodes let's say any electrolytes. So let's say the flow of current is these sides. This is the flow of current. Then the flow of electrons will be opposite to flow of current. Okay. So wherever if electron is flowing in these directions, then current will flow in this direction, opposite to electrons. This we know very well. This is very familiar. Okay. So now, what is some terms we are going to discuss? That is, first terms. Let's say the resistance. So we are very familiar about the terms. Okay, just a minute. Okay. So we are very familiar about what resistance. Resistance means which oppose the flow of electrons. Oppose the flow of electrons. So it means, and it is represented by R, and its units is ohm. Similarly, another terms, that is conductance. Conductance. What we mean by conductance? Conductance means which allow the flow of electrons. Allow the flow of electrons. Just opposite of resistance. And its unit is, and it is represented by C. And its unit is, since resistance and conductance are opposite, if resistance opposite means resistance is 1 by conductance, because they are opposite. So if resistance unit is ohm, then conductance will be 1 by ohm. So this can be written as ohm inverse. So its unit is ohm inverse, or you can write ohm inverse, or sometimes ohm inverse means mho, also written. Now this terms is fine, but whenever this resistance and conductance are not specific, means that are not normalized, so a new unit has came, that is specific resistance and specific conductance. For same, for this and this, a new unit comes which actually give you a specific value. So came one is specific resistance. Specific resistance, how can you say? R is equal to L by A. So from here, this formula we know from 10th class itself. So from here, specific resistance, or this is called resistivity. So this resistivity equal to R into A by A upon L. So how this formula has came? Let's say I have one electrode rods, and let's say electrolytes is there. Let's say any electrolyte, let's say NaCl. I use NaCl as electrolytes, and this is connected to a battery. Then let's say the distance between these two electrodes is, let's say, L. Distance between two electrode rod is, let's say, L. And another assumptions, area of this electrode rod, each electrode rod, let's say A square, because area means area of any square is side into side, A into A, so that is A square. So let's say we assume this is a square, so and then 1 unit, so let's say 1 unit, then 1 unit square. So we take 1 unit as A, side of each side is A, let's say this is a square, then A square. And if let's say this length is 1 centimeter, then 2 lengths L square will be L into L equal to L square. So we take each unit as A, then this will become A square. Okay, so since we are taking area, so let's say this is a square. Let's say one side is A, other side is A, then area is A into A, that is equal to A square. Okay, and if we say that this is A square, and if we say that each unit is 1 centimeter, let's say A equal to 1 centimeter, then A square equal to 1 centimeter square. And if we say that the distance between the length is L, and let's say this is 1 centimeter, then that volume will become area into length, and area we have A square, let's say length L, and this is equal to 1 centimeter, then L, and let's say this is each has 1 unit, 1 centimeter, let's say, then this is equal to 1 centimeter square, and let's say L is also 1 centimeter, then this is also 1 centimeter, so that is equal to 1 centimeter cube. 1 centimeter cube, that is equal to 1 milliliter. Yes. So what that specific resistance says that, so specific resistance definition, if you say the resistance offered to all the ions of an electrolyte present in 1 ml of solutions. So this is 1 ml. So since this is let's say this is 1 centimeter square and this is 1 L, so if I say in this specific area assumed, imagine this is actually a square and this all are in a let's say this all are this area where this so I'm taking this whole area as a volume, means this amount of area I'm taking like a volume, then what is the volume of this one, that will become 1 centimeter cube, because area is 1 centimeter square and length is 1 centimeter, that is equal to 1 centimeter cube. Then I take as 1 milliliter, because 1 centimeter cube equal to 1 milliliter. So what I says that if we take 1 unit cube from here, because this is 1 centimeter square area and this is also 1 centimeter square area, and distance between this is L, that is also 1 centimeter, then we can imagine that this will be like a cube, and a cube, since every side is 1 centimeter, height 1 centimeter, length 1 centimeter, breadth 1 centimeter, then this will become 1 centimeter cube, that is your 1 milliliter. So this amount of area means this amount of volume, whatever the resistance offered to all the ions of the electrolytes as NaCl to this ions like Na plus Cl minus, this will, due to this flow of this ions current will produce, or this flow of electrons will happen. So within this area, how many Na plus Cl minus, within this area, within this amount of volumes, the resistance upward to the flow of this Na and Cl minus of the electrolyte NaCl, and this is 1 millimeter 1 centimeter cube, the 1 milliliter volume. So within this volume, 1 milliliter volume, how much resistance upward to the ions of the electrolyte, that is called the specific resistance. Means we are not considering this area, we are considering only within this area. So within 1 millimeter of volumes, how much resistance upward to the electrolytes, ions of the electrolyte, let Na and Cl, for this NaCl electrolyte, how much resistance upward within 1 milliliter of volume, that is called the specific resistance. So previously we said that resistance means we not specified anything, so we say that if we get the resistance means this is not like not complete, means we not says that from where the resistance is this much. So this value will be buried, this resistance value, this is buried, but this value we say that the specific means within this 1 milliliter of solutions how much the resistance upper to the ions of the electrolytes, that is called specific resistance. So this value will be remain constant. That's why we say that this is specific resistance, or we can say this is intensive property. And this is extensive property. And what we say is that, and this resistivity of any substance or specific resistance or specific resistivity does not depend on the size of the materials. It depends on the material properties. So it depends only on material property. It means if gold is there, then the for that the specific resistance value may differ, and for copper the specific resistance value may differ. Means that if you change the electrolytes, or if you change the substances, then only the specific resistance value will change. Otherwise, if you not change, then the value will be remain constant. So it does not depend on size or amount of substances. So like here, if you take this amount of, means this beaker, let's say 20 ml beaker, other case we may take 50 ml of beaker. For that case also the specific resistance value will become same, because we are from there also we will consider only 1 milliliter volume of solution only we consider. So if you take here, and other cases if you take, I take bigger one. So if you vary the size, then also the resistance will be same, because we take here also the same things, one here also we will take that 1 milliliter of solutions. Means within this area how much resistance is happening. Okay, so this specific resistance value is a intensive properties which does not depend on the size or amount of the substances. It depends only on the material properties. And since resistance is 1 by conductance, similarly the specific resistance H comes to fix the resistance value. Specific resistance, this value come to fix resistance value or resistance offered to ions or to all ions of an electrolytes in 1 ml of solutions. This specific resistance comes to fix the resistance value, or that resistance offered to all the ions of an electrolyte in 1 milliliter of solutions. Similarly, So this comes to fix the resistance value. So, and resistance is 1 by conductance. So there has to be a word is there which is reciprocal to. So this is resistance is 1 by conductance, and the specific resistance comes to fix the resistance value. So similar case, a term H came, that is called conductance. So conductivity, which is reciprocal of this specific resistance, because resistance is 1 by conductance, or we can say conductance is 1 by resistance. So this resistance came for this to fix this resistance, specific conductance, specific resistance H came. So to fix this conductance also, a specific conductance H came, that is also again 1 by this value. Okay, 1 by this. Okay, so C and K are similar terms. C is conductance and kappa is specific conductance. Let me do. Please listen carefully that resistance, for to fix resistance, specific conductance is came. Similarly, for conductance, to fix conductance, conductivity H came. And for this relations is, this is 1 and this is 2. And resistance and conductance, this relations is R and C. The relations is R equal R is inversely proportional to resistance 1 by C. So same manner for R, that is specific conductance, and conductivity, the relations will be same. A resistance, this is equal to 1 by K. Okay. So we got that specific conductance, this is, so we already derived that specific resistance is this R into A by H. And one more things, yes, sorry, actually I left one thing. So this electrode rods, and between two electrode rod length is L, and this size of area of each electrode is A. So what he says that in a experiments, these rods are remain same, and the distance between the two rods also remains same, because while doing any experiments we maximum keep that electrodes distance between two electrodes will remain constant, and the size of area of each electrodes is remain constant, because we are just changing the electrolytes and all these things, and we are mainly used to keep the distance between two electrodes and the size of electrodes, that we remain fixed to get the specific value. So this value, so distance between two electrodes and the area of each electrodes remain constant. So this length of distance between electrodes is L, and area of electrodes, area of each electrode is A, and this is remain fixed. So what it says that if you divide L, which is length of electrodes, distance between two electrodes, and area of each electrodes, then this, since this value and this value are remain fixed, then the L upon A also remain fixed. So this value we call here as shear constant. Okay, this value we call as shear constant, and that resistance value, specific resistance value is resistance into shear constant. So this specific resistance equal to resistance into shear constant. So we get that specific resistance equal to R into L upon A. Sorry, R into L upon A. A upon L. A upon L. Then the conductance value. Conductance is 1 by specific resistance, and specific resistance is R 1 upon R into A upon L. So this will become 1 by R into L by A. So kappa equal to 1 by R is conductance, because conductance is 1 by R. So conductance, and L by A is shear constant. So this is A by L. This is not self. This is A by L. A by L is not self constant. L by A is self constant. So specific resistance equal to R into A by L. So this is the formula for conductance. So conductance is what? So as like we say that specific resistance comes to make the resistance constant. Similarly, conductance conductivity H or specific conductance H came to specify the conductance. So within this, if I draw here, and let's say electrolytes is there, and similarly if I say distance between two electrolyte is L and area of each electrolyte is L, then within this area, that is 1 milliliter of solution, how much conductance? Or within 1 ml of solutions, within 1 ml of solutions, within 1 ml of solution, conductance offered to all the ions of an electrolyte. That is called the specific conductance. Means conductance within 1 ml of a solution, or conductance within 1 centimeter of solution, 1 centimeter cube of the solutions. So specific resistance means resistance within 1 centimeter cube of solutions, and conductance means conductance apart within 1 ml of solutions to all the ions of the electrolytes. So this value, the conductance, this is value conductance, this is not fixed. So let's say if anybody says that this ohm inverse, then we actually not this value is not fixed and this is variable. So this is extensive property. Whereas this value is within 1 ml of solutions, how much conductance offered to the ions. So this conductance value is fixed, means within this 1 ml of solutions. So this is intensive property. Okay, and it only, so it is a material properties which does not depend on size or amount. Okay, so we understand that resistance for to fix the resistance, specific conductance is specific resistance is comes, and to fix the conductance, specific conductance is comes. So specific conductance, or also we can say conductivity. Now that this specific conductance is depend on the, this is conductance into cell constant, and this is 1 ml of solutions. So within 1 ml of solutions, how much conductance is offered to the ions, but we not say that concentrations. So this conductance, specific conductance, depend on the concentrations. It depend on concentration of ions of an electrolytes. It means that we says that specific conductance kappa, it is conductance offered to all ions in 1 ml of solutions, all ions of electrolytes in 1 ml of solutions. But we not say that in 1 ml how much concentrations of ions is present. So if the concentrations of ions is high, then the conductance will be increases. So this conductance is depend on the concentrations of the ions. So to fix the concentrations, another term has came, that is molar conductance. Molar conductance, it means the conductance, but in a 1 ml of solution, but in a 1 mole of solutions, means 1 ml means 1 mole, sorry, no, 1 molar means also we say 1 concentration. So within 1 molar of solutions, how many electrolytes is present? Let me say define. So molar conductance means kappa, this is conductivity into volume, where this volume has contained 1 molar of electrolytes. So the conductance, this is equal to molar conductance. So the conductivity of an electrolyte within 1 ml of, means this is defined by dm. So this is equal to conductivity into volume, and this volume has 1 molar of electrolytes. So it means that the conductance for to all ions of an electrolytes in 1 ml of solutions, or you can say 1 ml of solutions, or you can say in 1 molar of solutions. Instead of 1 ml, I says 1 molar of solutions. So what is the difference between that and this? Here I says that the concentrations of electrolytes each 1, means the concentrations, so 1 molar of concentration. 1 molar means number of moles by volume in liter. Okay, so if the number, so I say that in 1 molar of solutions, how many electrolytes may be present? So that electrolytes, the conductance offered to that amount of electrolytes, then that is called the molar conductance. Okay, so I fix that concentration in 1 mole. So within 1 moles, how much it upward the conductance, that is called molar conductance. Okay, and now somebody says that okay, you fix that concentration equal to 1 molar, then it is also possible that we can fix in normal 1 normal. So another term has comes, that is equivalent conductance. Another term has comes, that is equivalent conductance. So equivalent conductance means we can represent by n equivalent conductance, that is the specific conductance into volume, where in volume 1 normal of electrolyte is present. So if you are fixing that how much electrolytes is present. So within 1 molar of electrolytes is present, then that is called molar conductance. And if that 1 normal of electrolyte is present, then that is called equivalent conductance. So this is also conductance upward to all ions of electrolytes in 1 normal of solutions. So conductance upward to all ions of an electrolytes in 1 normal of solutions. Okay, these are the formula I can remember. So from here, if I say that m equal to number of moles by volume in liter. Okay, so in number of moles we take as 1. So 1 molar means what? We considering that number of moles equal to 1, then m equal to 1 upon v. Then I can say that here v equal to 1 by m. So here if I put, instead of v, if I put 1 by m, then this value will becomes how much? So it is fine, I have already give you. Then delta this m is equal to molar conductance equal to k into 1 by m, because v equal to 1 by m, so I will put 1 by m. So we can write this equal to k upon m. Similarly, this b for normalities, so normality equal to number of gram equivalents by volume in liter. And if we assume this as 1, then 1 by v in liter, then v equal to 1 by normality. So if we put here, then lambda equivalent equal to k upon n. So these are the formulas we will use. And the relationship between lambda m and molar conductance and molar equivalents. So we know this is very familiar, that is n equal to xm. How you remember? Because in alphabet m, first m come, after that n comes, so n is bigger, so what I write n into xm, because m is less, so if I multiply it x, then n will come. So this way you can remember, because n is come after m, so n is bigger than m alphabetically, so what I write n into xm. Okay, so this we know. So now what it says, and molar conductance equal to kappa by m, and molar equivalence equal to kappa by n. So if the ratio lambda m and lambda molar conductance and molar equivalence equal to k upon m by k upon n. So this cancel, so that will become what, n upon m, and n equal to xm, and this is n, so this is equal to x, অর্থাৎ lambda m or molar conductance divided by molar divided by equivalent conductance is equal to this. Okay, so molar conductance divided by equivalent conductance is equal to x factor. This is x factor, or we can say this is number of electrons. So this will be clear whenever we proceed these chapters. Okay, so today up to this. Thank you.